Alright, so we're looking at section 1.3, and this is evaluating limits analytically or symbolically. So, I've kind of chosen to go with symbolically when we start talking algebra. And here, the way we're going to evaluate these limits is we're going to take some limits as easy, right? We're going to decide things like, what's the limit as x goes to 2 of x squared. We're going to say that's easy. It's 4 because I just did a direct substitution. Okay, so this is direct substitution. And so we're pretty much going to say anytime we can do direct substitution and just look at the answer and know that everything was fine, we're going to say, yeah, we know that answer. Now we could also back this up a little bit with some graphics or a table, right? But I could go into something like Desmos, graph y equal x squared. There's 2, there's 4, and I would see that point is there, and everything's looks like it's heading toward that spot. Okay, so we're gonna decide when we can do direct substitution. We know the answer. We can do it, and we can get that answer. Now then, beyond that, we're going to use some properties to do anything more than that, or if we know one answer, and we can use one of these properties, then we'll go with that. And really, kind of from the direct substitution, one property is they're saying that if b is a constant, and C is another, so C and B are constant. Okay, so if we have that, then we can say some things also pretty confidently. The limit as x goes to C of B, that constant, is just B. Okay, well, think about it numerically, right? If I made my table of x's, here's an x1, here's an x2, and they're heading toward this C, and then, an x, whatever we get to here, 10, x11 or something, but I have a whole bunch of these x values, there's C. Well, then if it's the constant function, I would get B, B, B. Now, this is sort of my favorite thing because, what does that spell? Well, it spells right? So I can actually say what that is out loud. And but as you look at that, right, those are all B's. Of course, that's heading toward B. So check. Yep, that's kind of obvious. If I said, what's the limit as x goes to 5 of 7? It's 7. That's, we're going to go, yeah, sure, that's a no-brainer. Another property, so we aren't proving these properties, but we're saying they are terribly intuitive. Now the limit as x goes to C of x, the function x, well, that's just C. Well, again, that seems pretty obvious. We're looking at the function y equals x, so that's that thing, y equals x. And we're saying, hey, as I'm coming close to this spot here, then as I look at that, well, that's the same distance up here on the y-axis. So sure, yep, I believe that one. And then, now I just, substituted the x squared. They're trying to be a little pickier than that, and then they're saying, well, the limit as x goes to C of x to the n, well, where n is a positive integer, they point out, then that is c to the n, and that's kind of what I did up here by direct substitution. But on the whole, we're just going to say, hey, you know, if you can just plug the number in and it's obvious what you get, then that is the answer. You got to be a little careful, you know, so be careful about endpoints. You know, because if I said something like, well, what's the limit as x goes to 0 of the square root of x? Well, that does not exist. And I can plug 0 into the square root just fine. The problem is I can't plug anything to the left of 0. I can't put negative numbers in there. So you know, be careful about endpoints, but otherwise, you know, if I just ask what's the limit as x goes to 2 of the square root of x, oh, well, that's the square root of 2. Okay, so we can do that sort of thing. And then some more properties. This is at the bottom of page 59. Okay, and a lot of these are going to, I think, be reasonably intuitive. So if I know that the limit as x goes to, you know, some value c of my one function f of x is L. You know, I don't know what L is, but it's there. It's L, and the limit as x goes to c of g of x is k. So if I know that, then some things are, again, sort of intuitive. They seem maybe kind of obvious. And that is, you know, if I take the limit as x goes to c of some b times f of x, well, I can factor that b out of the limit. That's just b times the limit as x goes to c of f of x. And so that's just b times L. But I can pull that b outside of that limit. And that's pretty nice. Now, if we want the limit as x goes to c of f of x, either plus or minus g of x, doesn't matter which one, then we can separate this at the plus. So in other words, it's like the distributive property. I can distribute this limit over the sum or difference. And so I can say that this is just the limit as x goes to c of f of x, and then plus or minus the limit as x goes to c of g of x. And so that's L plus k. And, plus or minus k, depending on whether I was adding or subtracting. So that's really nice. Now the text doesn't really go into this middle part I'm saying here, but that's the mathematics. That's the stuff you want to get, is that a constant can be factored out of the limit. And a sum or a difference, if I'm taking the limit of that sum or difference, I can distribute that limit across that sum or difference and do these separately. And of course, if I had 3 or 4 or 5 things added together or subtracted, I could distribute across all of them. Okay, so I've got that scalar property, a real number. When you multiply by a real number, we tend to call that a scalar multiple, and so we can do that. We can distribute with that sum. Now, what's really cool is you don't always get something. The adding and subtracting in the scalar multiple, not really big news. You can often distribute something, you know, whether it's a limit or something else, over a plus or a minus, and you know, not a problem. So for instance, like in algebra, I can take a constant over, multiplying a sum and multiply each part of the sum by that constant, right, the distributive property. So that's not real big news. However, this is actually pretty big news, because often you cannot do something like this with various definitions of things, but with the limit we can. We can take the limit here as x goes to c of f of x, and we can multiply that by the limit as x goes to c of g of x. So in other words, we can distribute that limit operation, that limit concept, over a multiplication like this and get L times K. That's pretty significant, because many things you cannot do that sort of thing with. But others you can. I mean, something that you can, suppose I had x times y to the fifth, right? That's x to the fifth, y to the fifth. So there's a case where I can take that concept or operation that I'm doing and distribute it over a multiplication. So there are cases where you can, but it's just not as often that you see that. You see these first two much more often in many things. And then similarly, as long as the denominator doesn't go to 0, so we have this limit as x goes to c of the quotient here, f of x over g of x, as long as k is not 0, then we can do the limit of f of x, x goes to c of f of x divided by, and I'm just about out of room, I guess, limit as x goes to c of g of x, and that equals L over K, as long as K is not equal to 0, because we can't do that division. And then finally, the rule on powers. Now, this one, I don't think this is any great news here because of the product part, but we can also do powers. The limit as x goes to c of f of x to the n, well, that's the same thing as the limit as x goes to c of f of x all to the n that way, so that is L to the n. But again, that's not surprising, because if I took f times f, right, if this n is a 2, that's just f times f, and so we already knew we could separate those and do them each separately and then multiply the result together. So that wasn't anything earth-shattering, that number 5. Okay, so those are properties that we're using. And so they go through the limit of a polynomial, and they use all these properties. Well, I'm going to say, limit of a polynomial, so they have what? 4x squared plus 3. So they say, what's the limit as x goes to 2 of 4x squared plus 3? Okay, they go through and use all these properties, right? So first we have a sum. So this is the limit as x goes to 2 of 4x squared plus the limit as x goes to 2 of 3. Now I could evaluate this second limit at this point, but I can't quite do this one yet, but I can factor out the 4, so I get 4 times the limit as x goes to 2 of x squared plus 3. So I evaluated that limit. But then this is equal to 4 times the limit as x goes to 2 squared, plus 3, of x squared. And so that's equal to 4 times 2 squared plus 3. And so that's what, 16 plus 3, and that's 19. Now, if we use each and every one of the properties they gave us, that's what we get. That's nice, but I think at our level, that's just sort of silly. If you get something like this, limit as x goes to 2 of 4x squared plus 3, and you say that that is 4 times 4 or 2 squared or whatever, but you say 4 times 4 plus 3 because you're doing direct substitution, you know, and you say by direct substitution, I'm good with that. Okay, let's save the work for the ones where it's really just not obvious what the answer is. And let's look at you know, something like the limit as you know, x goes to 2 of what, x squared minus 4x minus 4 over x minus 2. Now, if I try to do direct substitution, right, I get 0 minus 8. Is that what I wanted? X. 0. Why did I say 0? I wish you people could speak up over this thing and say, hey, you just made a dumb error there. Well, be careful about calling things dumb, but I certainly made an error. So if I try to do direct substitution, I get 4 minus 8 minus, that should be a plus, that's what I wanted, plus 4 over 2 minus 2, but see, that's 0 over 0. So don't use an equal sign, because that limit is not equal to 0 over 0, because that is absolutely undefined, and it turns out this limit is not. And so what you should do when you're going to do this direct substitution, if you know it's going to work, go ahead and use equal signs. If you think it's not going to work because you're going to get something like 0 over 0, use an arrow, like a, you know, start that equal sign, but go, oh wait, I can't use an equal sign. Put an arrow on that thing and say, and this is kind of like this implies, right? So I'm not saying it's equal, I'm saying it implies that you have 0 over 0 if you do a direct substitution. And so that's no good. Well, now is when we can use our properties of limits. Is that I notice this is x minus 2 squared over x minus 2. But now that is the same thing as the limit as x goes to 2 of x minus 2 over x minus 2. So I'm taking one of the top x minus 2's and putting it with the bottom one, and then times, using our multiplication property, the limit as x goes to 2 of x minus 2, like that. Now, this first one here, well, that's obviously 1. Okay, because whatever I put in for x other than 2, I get the same thing on top as I get on the bottom, that's 1. So that's 1. And then this part, well, x going to 2, I can do direct substitution here, and that one is obviously 0, and so I get 0. So here's a case where 0 over 0 is 0. Okay? But if I turn this upside down, we would have had 1 times 1 over 0, which is undefined. So that would have been a case where 0 over 0, that the direct substitution idea anyway, would have led to a limit that does not exist, but in this case the limit is 0. Okay, this is where we want you to use these properties of multiplication and division and so forth. But here, very important, see, I didn't just cancel them out in here. I didn't just go, oh yeah, that's x minus 2 squared over x minus 2, get rid of the x minus 2's. I used the property that I can factor things and move limits along with it. So I took the x minus 2 over x minus 2 that I wanted to factor out, put that by itself, but then that limit is obviously 1. Okay, because again, for every x value other than 2, that evaluates to 1. So obviously, if I did that numerically, I'd get 1, 1, 1, 1, 1, 1, 1. That's going to 1. And then here, I can do a direct substitution and get 0, and so the answer is 0. Okay, so that's a good start to section 1.3, and we'll stop here with this video.